Okay, I'd like to show some activity with jump, starting with the regression to the origin table 4.2 example on the warehouse data, and then I'm going to do a few data sets from chapter 1, but go through them using the material through chapter 3. So starting with the warehouse table, let me get into jump. I already have the file loaded. There's a warehouse where there's various number of work units across 12 different warehouses, and this is a cost associated with those work units. Let's go ahead and to do the fit through the line, you do fit y by x. It's one way to do it. You do work units. It's a function of cost, and it looks pretty straight. And let's change the origin minimum to be 0 so we can really see it. Okay, and now do a fit with the constraint. We do fit special, constrain the intercept to be 0, and boom, there's the fit. And it looks like a pretty good fit. You don't do an r squared in this case, although you can see that the bulk of the sum of squares here are accounted for by the model. If we were to have just done a fit line and ignore the business of the intercept being constrained to be 0, notice then we get cost is 10 plus 4.6 times the number of work units. So there's a little bit of a difference at that end. Now I can save the predicteds here, save predicteds here, and then have a look. And you see there's some difference, anywhere from 10 to a couple, 6, and so forth. So they're fairly similar fits. It looks like a pretty decent fit. So that's one thing I wanted to do in this little video. The second one is to pick each of these 3 examples. This is the kind of stuff I expect to be able to do without any trouble. And when people are asking what should they be doing, yeah, you can read the book for reinforcement of the material covered in class. I also have recommended you take each data set mentioned in the text. These data sets are available, and go ahead and run the fits and investigate these data sets as thoroughly as possible. So let's take the copy maintenance data from problem 1.20. And I have that file here, 120. There's 45 observations. There's various number of copiers that have been or need to be serviced, and this is how much time it took the person to service them. I've already looked at this data set, so that's why this column is here. I can get it out of the way if it's bothersome. Okay, so we want to regress y service time on x copiers. Analyze, we can do fit model. I'll do fit model because I want to look at box Cox, for example. So x copiers is the model effect or the variable. Y service time is the response. Do screening. Run. And let's see what kind of stuff. Looks like service time versus copiers looks like a pretty decent fit. If we look down here at lack of fit, F ratio under 1, it's always a good sign. And so it looks like a decent fit. We shouldn't really have any difficulties. I mean, it looks like a reasonable fit. We could certainly save the residuals for later consideration. Do they look normal? That's just kind of tidying things up and with respect to the assumptions. Also, let's have a look at the box-Cox transformation. We'd be kind of flabbergasted if a transformation is called for. Let's see what happens. If we do it, you'll notice, unlike some of the canned examples, the curve is a little hard to make out. It's like the scale, the vertical scale is difficult to read. So I'm going to change the vertical scale by putting the cursor on the numbers and then resetting the maximum. Tell you what, let's get rid of 3 zeros, both for the max and increment. See if that helps us get a better looking plot. Sure did. Of course, previously I had done it 1 0 at a time to realize that was the way to go. Let's stretch this out. a little easier to see. And then you can use the crosshairs under Tools to check just where 1 is. A value of 1 for lambda indicates no need for a transformation. So it makes it in there. Probably no need to do anything with that. And since we still have that same data file open, we could quickly check the residuals. This is the one I just saved. Done this before. And then have a look at the normality fit by doing continuous fit, normal, and then check the goodness of fit. Shapiro-Wilk test, 0.46 p-value, no problem. So basically, this thing's in good shape. Going back here to the plot, let's see if we had any. Wanted to stick the other plots in here. We could look at, say, residual by predicted. Have a look at that plot, and looks like pretty uninteresting. One might imagine some kind of curve, but there's quite a bit of variability vertically, so I don't see that this is more of a tunnel than any kind of a funnel or curved horn. So that's one of the data sets. Let's have a look at air freight baggage, which is 1.21, problem 1.21. I have that file open here, air freight baggage. And again, I've done some stuff with this, but so just bear with me, it's on there. Here's the number of breaks of beakers or something as a function of the number of transfers of this material from one, I guess, airport to another. So let's just fit this guy. Fit model X is my explanatory variable, Y is the response variable. Screening, let it run. Again, we have lack of fit. Wow, lack of fit is like tiny, 0.17, so really virtually no lack of fit. If we look at box Cox, again, just for confirmation rather than suggesting, oh, there might be a transformation called for. And you see here, I'll move it up. 1 is right here, well within the intersection of the lower left boundary point of the confidence interval for lambda. We have a pretty small sample size, so that's why this width is pretty broad. Okay, I guess I can also save the residuals. I've done that previously, and we've done this a number of times. Let's just have a quick look at them. It's such a small sample size, it's hard to reject normality, even though the histogram looks kind of less than perhaps normal looking. But with small sample sizes, you have to have fairly significant differences in order to pick up something that's non-normal. Here's the p-value, 0.26. So no issues there. And had I done a plot of, I have it, okay, we already did that, sorry, residuals by predicted. Oh, this is back on problem 20. Let me go to this guy, get rid of this. I want to do 21. Let me close 20. Let's see here. Here's my, here was the fitted one for air freight baggage. I look at the plot of residual by predicted. Oh, I don't know. There's just a single data point here, so that's not going to help us one way or the other. It's basically pretty flat, pretty much like a tunnel. If I notice I have an extra column X transfers categorical. I've just copied these numbers under X transforms into categorical into another column and then changed it to categorical. You see the red histogram here, meaning the data is modeled at nominal. Here it's modeled as continuous. So I can do tests for homogeneity of variances via the residuals. as a function of those categories. Even with the category that has a single observation and a variance of 0, it doesn't hurt anything. And we do unequal variances, and we see the p-values, regardless of which test is, they're all well above a nominal 0.05, so there's no evidence to suspect that there's a difference in variance. All again, these sample sizes are extremely small. And last but not least, the plastic hardness data set, problem 1.22. Let's have a look at that data. Here, oops, wrong one. Close these. Problem 22. So we have 16 observations. This was actually a designed experiment looking at 16, 24, 32, and 40 minutes, manufacturing an item, and then test the hardness later on. It kind of looks like the hardness is better the longer the X time was. We can do a fit, analyze fit model, hardness versus time, do screening, lack of fit, no problem, F ratio 0.82. So all of these are good fits. I mean, this is not too surprising. They wouldn't give us fits in the first few chapters and have major problems and not immediately provide mechanisms for correcting them aside from Box-Cox. Certainly if the variances are unequal, we're not quite ready to do weighted least squares. So what's to be done? I guess we can, as usual, look at residuals by predicted. That looks pretty ordinary, pretty flat, and we can do a Box-Cox analysis. Again, we wouldn't expect to see much, and even without having to rescale anything, move it up. Here's the value 1, well below the intersection. So this is the confidence band, anything pretty much bigger than 0.25. So it's a very wide band. 1's in there, so that means basically leave it alone. So with that, that's to give you some practice with what could be done with these data sets, and you should do as many of these as you can to get some practice on it.